And excellent. Somebody from Dortmund coming in fourth here. Great. So our next talk is about excitability, anesthesia, and reception from thermodynamic perspective. Thank you.
Thank you. Good morning. In my talk today, I'd like to address some fundamental properties of cells and how they may be explained in a very unifying manner, as I think, with little assumptions based on thermodynamic concepts. One property of interest in cells, and as Martin indicated yesterday, this is a property that many cells seem to have, is that if you stimulate cells, there's a pulse propagating in the membrane. This pulse is called in biology the actual potential, and this pulse has been observed in a variety of cells. Characteristic properties of this pulse.
Some competition.
Sure.
You want to take that one? I'm sure. Does yours work? Right. Does it have it? I think it does.
Okay. I mean, we've heard about this before. Some characteristic properties of these pulses are that they have a threshold and saturate. The amplitude saturates upon excitation. This is typically called the all or none response, and these pulses, if they meet each other, they annihilate. At the same time, and we've heard about this yesterday as well, very, very similar pulses are observed close to a transition in lipid monolayers. These pulses also have an all or none behavior in the same sense as actual potentials to have it, or to exhibit it, and these pulses collide upon annihilation. Now, if one wants to understand the origin of both responses, the response in the cell membrane and the response in the lipid membrane, I think it's quite correct. I think it's very clear that the origin of the response cannot reside in a specific molecule, because the specific molecules in the molecules which compose the different systems, the lipid monolayer on the one hand side and the cell membrane on the other side, they are very different. So the origin must be something more abstract. And as has been highlighted yesterday, we think it's reasonable to resort to thermodynamics to find the origin of both of these phenomena. And the one who pioneered this approach is Connie, who sits here, and who suggested in 1989 that that the response of a system to perturbations is nothing to be surprised of. And usually this response will be a linear response, so a linear stimulus response curve. However, if the material has a transition, and he was particularly interested in biological membranes, and if the membrane has a transition, this can lead to a nonlinear response. And this theory has been elaborated on, most notably by Thomas Heimburg, who talked about this yesterday, and also by others from a theoretical perspective. Now in the talk, we want to take this theory as a starting point, and we want to derive biological consequences from it. We assume that the cellular resting state, the typical resting state of a cell as it's found in biology, that this state is indeed close to a transition in the membrane material. Okay? And if you put the cellular resting state in a phase space, and this transition close to the cellular resting state will make phase space and the relation between the transition and the resting state asymmetric. And this asymmetry has consequences for the cell or for this material. One consequence will be the nonlinear excitability, the nonlinear stimulus response. Another consequence, as I would like to argue, is that anesthesia or the loss of this nonlinear excitability is something that you wouldn't observe or wouldn't claim to be observing in a linear system, but is very characteristic for a system close to a transition. And thirdly, the typical relation between transition and resting state leads to natural stimuli which will simply favor a change of state towards the transition. And these natural stimuli, we would like to, in my talk, also like to rationalize what are typical natural stimuli for cell membranes. So we want to, So, and I think these latter 2 points, for those of you who are more interested in biology or pharmacology, these latter 2 points are very inherently connected. And this relates to an old pharmacological rule, as formulated here by John Newport Langley, who was one of the originators of the receptor concept. As he pointed out in 1906 already, it is extremely common for drugs to stimulate first and then to paralyze. Okay? And I think this is very inherently connected. And I would like to show you why I think that. And so we want to approach these questions and these phenomena based on phase diagrams, because I think there are very intuitive interpretations for these phenomena. And now, for us, the phenomenon of interest is the action potential. It's a pulse propagating, or it is associated definitely with the cellular membrane. It's a macroscopic phenomenon. And the macroscopic system that forms the cell membrane in the first place is the lipid bilayer, with proteins, sugars, and whatever else molecules are in there. So it's reasonable to start from a macroscopic system, and this is the first system that comes to mind is the lipid membrane. Now what one can do is basically take a temperature, three-dimensional pressure, projection of phase space. This phase space is so far empty, and we simply place the cellular resting state into this phase space. And if one basically wants to now understand the phase space of an excitable membrane, ideally one would have the state diagrams of excitable membranes. But these diagrams are not available at the moment. So what we have to do now is make an educated guess how their phase diagrams may look like. And basically we want to compare this with real biological phenomena and see if this guess was more or less right or wrong. Okay? One transition that's very prominent, and it's exhibited by many different lipid membranes that have been studied, a lot have been studied. One typical transition would be if we assume that the cellular membrane is indeed in a fluid state, and this is argued by everybody in the field. One typical transition would be the transition from the liquid expanded phase in lipid monolayer terminology or the fluid phase in bilayer terminology to the liquid condensed or gel phase in monolayer and bilayer terminology respectively. And these two phases are separated by a coexistence regime. The lipid condensed phase then is exceedingly complex. There are different gel phases, so we abstract this a little bit. And these phase diagrams are basically, usually how you obtain the phase diagram is from state diagrams. So for example, a state diagram along the arrow indicated here. This would be an isotherm in this case, and the state diagram here exhibits a typical inflection point, which is characteristic for a transition. And the consequences of the transition may become even more obvious if you take the derivative of this state diagram, where you obtain the susceptibilities or material properties here in a mechanical representation, the compressibility of the system, and in this sense, the resting state, the typical resting cellular resting state would be assumed or presumed to be close to this transition, or this maximum in susceptibilities. So what we simply say is we take the assumption that the fluid phase above this transition, this is called the excitable regime. Okay? And we assume that the cell is indeed near transition. All excitable cells are near transition. And this transition can be approached by cooling the system at constant pressure or by pressurizing at constant temperature, or combinations of these parameters. However, the phenomenology of phospholipid membranes is even more rich. Okay? And this is just one more aspect. But I think it's a very fundamental and important aspect. Typically, lipid molecules, phospholipids and others, at their head group have acid and base functionalities. So they basically are susceptible to taking up or releasing protons. And this PK of the molecule, or the protonation transition of the head group, it confers upon the membrane interface an additional nonlinearity. So now we don't just deal with one linearity, but with an additional one, the protonation transition. So we again look at our phase space. Now there's a projection of phase space in the temperature pH axis. Of the temperature and pH axis, we again assume that the resting state is in the fluid phase. And now the important point about the protonation transition is that the transition temperature of the material now is not constant as a function of pH, but it has a dependency on pH. Okay? And this dependency for typical phospholipid membranes is sigmoidal, so it's a typically a sigmoidal dependency of the transition temperature. So what this means is that if we have the excitable regime again denoted in the fluid phase, that one can induce a transition of the membrane material at constant temperature and pressure simply by decreasing the pH, which would be equivalent to the trajectory in phase space as indicated by this arrow. So the assumption is that the transition can also be approached by acidification of the cell, or the external medium of the cell. So we shortly want to summarize some of these predictions based on our putative, so far, phase diagrams. We assume that cooling, pressurization, and acidification of the cell take its membrane material towards a transition. And if this state change is a rapid parameter change, this will lead to triggering of an action potential by properly pulse. If it is a slow parameter change, so if you slowly cool the cell, for example, we think that a particular signature of the point when you hit the transition or when you come into the transition regime is that there will be a decrease of the pulse velocity. And Thomas Heimburg went into this yesterday, so I will only keep this very short. At the phase boundary, you usually expect an increase in compressibility, and if you move the cellular resting state towards the phase boundary, into the phase boundary, you should actually see a characteristic slowing down of pulses because compressibility becomes larger. Anesthesia, or the loss of excitability, is something that will ensue, as I would like to argue, if you actually take the cellular resting state into the other phase. And I will explain later on why I think that would lead to anesthesia. So we want to understand these phenomena. We first start with slow state changes and want to observe what happens in cells if you for example, change the temperature of the cell. Now here we have data from different animals and plants, and they are basically, what these data are showing is the normalized velocity of action potentials as a function of temperature. Okay? And as these curves, and let me walk you through them, they have some very characteristics and common features between animal and plant cells. One characteristic feature is that if you take the typical growth temperature, and I explained it in case of the plant cell, for which the typical growth temperature is at about 20 degrees Celsius, if you take such a cell and cool it down and observe the pulse velocity, you see a characteristic slowing down. Okay? And this is something that's a feature that you observe in axons as well. And there are, to my knowledge, no exclusions. So there is a typical decrease of action potential velocity upon cooling, and this is followed in many systems by a loss of excitability. And in the literature, this phenomenon is called cold block. Okay? And this is in expectation exactly from our phase diagrams so far. Something that was quite unexpected for us is if you heat up a cell, the action potential velocity is increased, and at some point the cell actually the velocity decreases and the cell loses excitability. And in the literature, this is referred to as the heat block. And this is a correction that we will have to add to our phase diagrams later on. Now, two other parameters of interest are the bulk pressure and the proton chemical potential. So for the bulk pressure, we don't have a lot of data available, but there were studies in the early 30s to 1950s by Harry Kunfest, for example, and also by Tasaki and one of his collaborators, Spiropoulos. And these studies are more or less in agreement that there is, upon pressurization of a cell, and for that you actually need hundreds of atmospheres, a decrease of pulse velocity and finally also loss of excitability if you pressurize the cell. Okay? And this is also something that we expect based on our phase diagrams, as proposed before. For data concerning the pH or proton chemical potential, this is work by Anne Pega. We again studied these excitable plant cells and basically changed the pH of the extracellular medium. And what you observe is if you go from pH 7 to the alkaline side, there are almost no changes in pulse velocity. However, you acidify the external medium of the cell, there's a progressive slowing down of pulses, and at about pH 4.5, the cell is apparently inexcitable. This third point as well is exactly in agreement with what we expect from the phase diagrams. Now, an interesting point about the thermodynamic frame is that you can also change state, obviously, and migrate between phases by combinations of variables. Okay, and this has some interesting points in itself, because it can, for example, show if the states in your system that you actually study, if they are somewhat stable. Okay, because if you make, for example, a circulatory change of state in phase space, you would expect, if the states are somewhat stable, that after the circular change, you arrive at the initial state. Okay? Another point of interest of such a circular excursion would be, is it really possible to compensate different parameter changes? Okay, so for example, can you compensate the parameter changes induced by temperature? Can you compensate them by changes of pH or by three-dimensional pressure? And to do such an excursion in phase space is definitely possible experimentally. And what we would expect based on the argument with compressibility is, for example, that if one acidifies the cell, basically transports the resting state into a transition regime, the pulses should slow down. Then you can heat up the cell, kind of take it out of the transition again, pulses should speed up again, change pH back to regular, you get even further into the fluid phase, the pulses should speed up. And then finally, by a change of temperature at constant pH, you should get back to the initial resting state. So the feasibility of such an experiment is something we examined. We basically did exactly this cycle with an excitable plant cells, and the actual results in terms of velocity are exactly what we predicted. Okay. Another point of interest relates to the stable states, at least within the time frame of this experiment, which is about 2 to 3 hours. You actually do return to the initial state. Okay. So you do not end up in a very different state. And one prediction based on these arguments would be, for example, that an acid or high pressure block induced in the cell can be reversed by heating. Okay? And there are other predictions which I do not go into detail at the moment. So now we can return to the phase diagrams that we proposed initially and kind of revise them, see where we were wrong, and introduce corrections if that is necessary. So what we basically predict is that we, by observing the parameter changes that are needed to induce this loss of excitability, we basically predict that this is the actual location, or that these parameter changes can be used to localize the phase boundary of the cellular membrane material. Okay? So we actually observed that the cooling by 15 to 35 degrees Celsius, the variation is so large now because I basically pool data from many different preparations, from excitable plant cells, many different neurons and myocytes into one type of parameter range here. Okay? For one system, it's much more defined. So we basically assume that the transition is hit in these systems if you cool the material down by 15 to 35 degrees Celsius. An interesting point that we didn't consider previously was that there may be an additional transition at higher temperature. And this is, as we think, something that may underline the heat block phenomenon. For three-dimensional pressure, there are a little bit less data available, but it seems that the range, based on also some other papers, is somewhere about 800 atmospheres. So you hit the transition of the membrane material if you pressurize the cell by several hundred atmospheres. And for pH, there's also a large variation. Again, this is because I pool different systems now. If you acidify the membrane by 1 to 3 units, you should hit the transition. And these are quantitative predictions. Okay? So if you study the cellular membrane and you do not find a transition in this regime, basically the theory, or at least my interpretation of it is out of the window. Okay? So there are quantitative predictions here. Are there any indications that membranes, biological membranes, really have transitions? Thomas Heimburg talked about this yesterday, so I only will go over this shortly. Indeed, in many different materials, ranging from bacteria to plants to human material, there are indications that transitions take place in the membrane material about 10 to 30 degrees in growth temperature. And if you recall the previous slide, this is more or less exactly the range that we predicted based on measurements of very different properties, namely excitability and velocity. But one can go into a bit further quantitative detail based on these phase diagrams. So what we basically propose is that the loss of excitability demarks the phase boundary, or the location of the phase boundary. And if you basically take these locations, the location of the phase boundary by two different parameters, you can get the slope of the phase boundary. And the slope of the phase boundary is something very characteristic, and unfortunately, this is a parameter which has been also obtained for many different lipid membranes already. I will call these thermodynamic coefficients, and we simply calculate them by dividing these parameter changes. So there's a characteristic relation between temperature and pressure in the material. There's a characteristic relation between temperature and pH. And if one compares these coefficients as obtained in cells from very different measurements with the coefficients from state diagrams of phospholipid membranes, one finds that there's a very striking quantitative agreement between these data. Okay. And this really suggests that the two-dimensional membrane interface plays the main role in cellular excitability. Now, I would like to spend some words on the origin of anesthesia, nerve block, but also, and I think this is also related to a phenomenon typically in synapses that's called desensitization. Okay? I think there are two different means to induce anesthesia or loss of excitability in cells. Okay? One means is to take the cellular resting state across the transition regime into the new phase. Because then the typical natural stimuli for this system will take the system just further away from the transition into that phase. They will not go back to the transition. And I think this is the physical origin of the phenomena that the people call cold block, pressure block, or pH block in the literature. Okay? However, and this is something that Thomas went into detail yesterday, so I will not spend many words of it on it. There's also another mechanism, especially in such a system close to a transition, which can induce a phenomenon like a loss of nonlinear response, which is to simply remove the resting state or to increase the distance between resting state and transition. But this loss of excitability must be compensatable by an increased stimulus strength, and this was indeed shown. For the first type of block, for the first type of loss of excitability, this is not possible. That would be the prediction. That even if you stimulate the systems harder, you will not regain the nonlinear excitability. At least not the same. So I think one intuitive conclusion from these observing the phase diagrams and the resting state in relation to the transition is that there must be two qualitatively different forms of anesthesia. And if you go to the literature, people actually were very confused about the mechanisms of anesthesia because they tried to fit both of these into the same mechanism. Now there's another point of interest which we also touched upon yesterday, namely, is nonlinear excitability really gone in the condensed phase? Okay? So what we did initially is we denoted the fluid phase as the excitable regime. Was this now justified? So for example, if one can create a situation in which one actually can take the resting state into the other phase, what would we actually predict would happen there? Would nonlinear excitability really be gone? So in the typical resting state, the nonlinear response in cells is induced by an outward membrane current. Okay? And our prediction would be that if you can actually generate a resting state in the opposite, so if you can basically transport the resting state into the other phase, the symmetry reverses between resting state and transition. So one should actually, in this depolarized resting state, which is indeed something that can be induced in cells. I don't know the biological relevance, if it's really a relevant thing, but you can induce it in cells, and many people have shown that amongst each other. Amongst those, Tasaki was a very careful experimenter, but others did it too. For example, if you take, in this case, a Purkinje fiber and you cool this fiber, you can actually observe that the cellular resting potential is depolarized. Okay, at first there's a spike here, and then it stays on a depolarized level. And this level is stable over extended periods of time. And in exactly such cells, you can test that. So now what we basically assume is that this depolarized potential level is a new resting state, opposite side of the transition. And the prediction would be that now actually the very inverted natural stimuli should excite the cell or should induce a nonlinear response. And this is indeed observed. And in the literature, this phenomenon is called hyperpolarization. It has different names. By most people, it's called hyperpolarizing response or inverted action potentials. Different groups have shown that this is the case, that you actually, from this depolarized resting potential level, you can get all or none pulses that propagate in cells. So it may be more accurate to call to not only call this part of phase space an excitable regime, but actually also other sides of the transition, excitable regimes. But these regimes will have different natural stimuli. Now, I would shortly like to go to the triggering of the nonlinear response. The assumption is that the action potential can be induced by rapid parameter changes that take the system towards the transition. One such parameter change obviously would be to cool the system locally. And we studied this with the excitable plant cells. We basically took the cell at 20 degrees Celsius and locally exposed it to cool medium. Okay? And depending on the temperature difference between 20 degrees Celsius and the medium we added, we at first saw no response. And then, if you cool the cell by on average about 10 to 15 degrees Celsius locally, you observe the appearance of an action potential. So you can trigger action potentials by cooling. And it's something, if you go to the literature, there are very few explicit studies about it, but in a note, Tasaki said that this is a very common phenomenon. Now these thermodynamic coefficients that I mentioned previously, they come in handy, because if you have this stimulation threshold for one parameter change, you can at least make very rough estimates of the parameter changes, other parameter changes necessary to induce the nonlinear response. So for three-dimensional pressure, based on these thermodynamic coefficients we calculated, the predicted threshold would be in the range of somewhere between 500 and 700 atmospheres, and the experimental findings are not that far off. They're actually in a very similar range. And the same is for pH. Depending on the system, the threshold should be somewhere in the range of 1 to 3 units of acidification, and this is what you observe in practice as well. Now, concerning the sensitivity of cells to protons, I would like to spend some more words on it. We have mainly been interested in neurons so far in this conference, and if one actually dives into the literature, one finds that neurons are almost all neurons studied. There are some exceptions, but many neurons studied, and other cells too are responsive to protons. What is the typical response of neurons to protons? Neurons are excited by protons. So if you take a cell and you clamp the membrane voltage and expose the cell to acidic conditions, you see an inward current. And this inward current is usually proportional to a depolarization of the cell. If you want to study different neurons, one finds that the pH sensitivity may differ. And if one doesn't voltage clamp the neuron, but simply observes membrane potential, as in this study, one can show that if you acidify the external medium of the cell, you can trigger multiple action potentials. Okay? So the literature here is in agreement that acidification of neurons results in depolarization and triggering of action potentials. And now I think this has some relevance for the cholinergic synapse, which, at least according to my knowledge of the literature, has not been addressed adequately up to date. So the present theory for the cholinergic synapse is that you have two cells impeding on each other, basically separated by the synaptic cleft, as illustrated here. A nerve pulse propagating along one cell leads to the liberation of the neurotransmitter. In this case, this is the substance acetylcholine, which Silly was talking about right before me. The neurotransmitter is supposed to diffuse across the synaptic cleft, bind to receptor molecules on the postsynaptic cell, And in the third and final step of this sequence of events, the neurotransmitter is hydrolyzed by an enzyme which is one of the fastest enzymes that we have found in nature, acetylcholinesterase. And in the textbook theory, this is basically mentioned as a mechanism to inactivate acetylcholine. Yes? Yeah, thanks. I will speed up. So I have a problem with this, to call this an inactivation, and the reason why I have a problem with this is because of what I presented before. During this reaction, when acetylcholine is hydrolyzed, acetic acid is generated. And the synapse, there's no way around it, must become acidic during this reaction. So hydrolysis of acetylcholine releases protons, and protons excite neurons, so there is a large likelihood that this excites the postsynaptic membrane, and this was indeed proposed by Connie as a mechanism of cholinergic synapses. So we were curious to study if it's possible to make cells responsive to acetylcholine in absence of receptor proteins. Okay? And the fortunate circumstance came to our hand that these excitable plant cells we have been working with all along do not respond to acetylcholine. Now here the membrane potential dipolar, or the depolarization of the membrane is plotted as a function of concentration. If one adds esterase and basically hydrolyzes acetylcholine, one observes with increasing hydrolysis a very prominent depolarization of the membrane and triggering of action potentials. So an hydrolysate of acetylcholine actually makes this cell responsive. So the presence of esterase makes this cell responsive to acetylcholine, and this is because of the generation of protons. And I think it's something that hasn't been dealt with adequately in the cholinergic literature, to my knowledge. So I would like to conclude and present a short outlook. We proposed some phase diagrams in different representations that rationalize the location of the transition. We have quantitative predictions for this, reception of the natural susceptibility of membranes to stimuli as state changes towards a transition. There must be two different forms of loss of excitability, and one may call this anesthesia. And I think that the type of phenomenon that Langley was talking about belongs to the first type of category. What we would like to work on now is we would like to better understand the implications of the transition for other membrane functions as well, and for the stability of the organism and for the cell. And finally, and this is an unresolved question, a very fundamental question that has not received an answer so far, how does the living system even localize itself close to such a transition? And with this, I would like to thank in particular Matthias for support over the years in various ways, Connie for theoretical inspiration and many discussions, and my friends and colleagues for many valuable discussions and valuable hours together. Finally, for non-scientific support, which is very important, I thank my wife and daughter, and now you for your attention.
Thank you very much. We have a couple. It was the fastest one, sorry.
Just more a statement than a question. The parameter ranges you have given here are by sure lipid dependent, correct? The parameter ranges for the numbers you have given here, the temperatures 5 to 35 degrees pH and so on, are by sure lipid dependent, because when you use we have discussed it, when you change to significantly different lipids, I'm thinking for example in this Excitable story, you will have an extended parameter range for your story, I think.
Definitely. So what we basically take here are the typical resting states with buffers that you use in cell experimental physiology.
Typical vertebrate biology also. I think this is important to state. All these things are more or less correlated to a specific lipid composition, which has this very typical phase transition in temperature ranges and in pressure ranges we know. Because biology is a little bit more than that. Biology can go beyond that, okay?
You can play around with, I don't mean to say that the membrane is just lipids. The membrane is formed by lipids, but there are proteins there are sugars there, and all of these, they will play around with the phase diagrams in very funky manner, possibly. But I would predict that if the resting state is too far from the transition, you won't observe this phenomena. in these cellular states.
And then a second nasty statement, you know it anyhow. This statement about the cholinergic esterase by sure is correct what you said. But on the other hand, you can excite membranes with acetylcholine receptor by nicotine, and this does not produce protons.
So I think one can go into more detail there, but the question is, what did physiology, or what evolved in nature as a mechanism of the synapse? And I don't think nicotine was there, acetylcholine was used, esterase, and butyrylcholine esterase is there. So I think it's a valid thing to consider. There may be other mechanisms too, and the receptor proteins may be related to those as well.
Thomas, it was first before. Sorry, Thomas, you've been overwritten by.
Sorry. Thanks for the nice talk. I just have a more generalized question. So regarding the diagram you showed on how action potential speed depends on the change of, I think, pH and the temperature.
Okay.
I just wonder if you know how in these experiments the speed of action potential is measured.
How it's measured?
Yeah.
What you basically do is the cell is a long cylindrical object, and you basically seal external portions of the cell electrically with vaseline, and thereby you can measure the appearance of the pulse in space at different positions in space. So if you have a pulse propagating along the cylinder, it will appear first at the first sensor, and then after a characteristic delay at the second sensor. And if you know the distance and the delay time, you can calculate those.
Yeah. Okay. Thanks. So my actual question is.
Oh, okay. Sorry.
So basically, the fundamental assumption is action potential is thermodynamic pulse. So when you talk about measurement of the velocity of action potential, you actually measure the electrical pulse. So I was wondering, will it be more convincing if you can directly measure the pressure change or pH change or temperature change at the other end, so that you can directly prove that the action potential is the thermodynamic pulse rather than measure the electrical.
So I think it's not a contradiction to use the electrical manifestation. So in the thermodynamic theory, the electricity is nothing separate. It's part of the same phenomenon. So the mechanical, thermal, optical, and electrical aspects, they are part of this phenomenon. They are inseparable. So I think it's valid to simply use one manifestation to measure certain properties, as long as you consider that the rest is there too. And one could do this mechanically. I wouldn't expect that there are main differences. One could do it, it's just more complicated. Because you have to set up the measurements.
You asked in the end the question how the living system maintains the phase transition.
Yeah.
But I mean, just like the acetylcholine esterase, there's a lot of phospholipases that are known to be active only in the transition. So I personally believe it's auto-regulated. If the system is in the transition, all kinds of enzymes become active and change the lipid composition until you are out of the transition, and that's exactly why you find all these living systems exactly at the upper edge of a transition. I think it's just a self-regulated process where you don't have to think very much about how it happens.
And I have a couple of reasons why I think it's not that simple, and I'd be happy to discuss them. And maybe also to hear your point of view how it happens. We discussed this quite a bit. I think it's a bit simple to simply say it's related to enzyme activity, because after all, enzymes just catalyze the reaction itself. If you actually want to substantially shift the composition of lipids from hydrolyzed to synthesis, or synthesized state to hydrolyzed state, or whatever you want to do, the reaction will only happen if the conditions favor it. The enzyme just makes it happen, but it cannot, step in and say, okay, let's make more double bonds now. If the ambient conditions don't allow for this, the enzyme can't do anything about it. So I think it's not that simple.
I have a question, actually. It's to you and maybe the wider community. So there's a lot of work about the excitability and phase transition, and under which, and also relates to Thomas' work, under which you can excite the cell and above which you come. But has there been any work on ion channel activity and try to look at different thermodynamic conditions under which ion can freely flow through the ion channel, or I stopped from doing so because there's too high temperature or too low diffusion linked to too low temperature or something like that. So I agree that there, in my view, I'm a bit of an engineering here, on the engineering side here. My view is that there might be a mix of physics going on simultaneously. But that maybe one reinforces the other in the sense that they might appear, maybe evolution is such that the phase transition lipid correspond also to a state at which ion channel somehow varies their functioning based on different thermodynamic configuration.
Okay.
So has there been any parallel work done on the ion channel, doing pretty much what you're doing, to try to see if there's such thing as phase transition?
I'm not sure. The literature is huge. So I would like to go back to the initial point that we wanted to make. We wanted to make as little assumptions as possible about the actual molecules in the system. So this is something that most people won't be satisfied with because we want to understand what the molecule does. So we try to avoid this. We try to understand the material, how it is, and if one embeds proteins in there, the phase diagrams may change. They may change in peculiar and funky manners, and I think this is very little understood.
But I'm talking not necessarily embedding ion channel in membrane, which you'll have to do anyway, but focusing exclusively on the ion channel. And trying to see how, if you were to look on the ion channel, maybe it's molecular dynamic question, I don't know, but if you were to focus on the ion channel and put a cloud of ions on top and underneath, and change the temperature, would the functioning of the ion channel be varying in a similar fashion as the membrane around is varying? And there's essentially some kind of resonance in between the functioning of the ion channel themselves, the membrane themselves, which means that the physics work all together.
I think it's difficult to do this experiment, to isolate something that's in a membrane and study it by itself. So maybe possible in a simulation, but then the question is this related to reality or not?
So you mentioned the heat block and that this is caused by another phase transition. I
put a question mark there.
Yeah, you barely touched it. That's why I'm asking.
Yeah.
So is there literature out of there, like something similar as the hyperpolarization, like a hypo? I don't know.
So what you observe is if you take the cell to this range of temperatures around the heat block, you see depolarization in a step-like fashion, often sometimes with oscillatory excitation of pulses. And if you cool it down quickly, this is reversible. But if you keep the cell up there, this becomes irreversible. And in my opinion, there are a couple of hypotheses you can make about it. If you look towards the phase diagrams of lipid, at higher temperatures, lipids often have a transition to the hexagonal phase. Now, this is difficult to imagine with an isolated bilayer, but if such a transition may happen in biological materials, and some people suggest that it may do, then this would destabilize the bilayer and may lead to something like the heat block. But in the calorimetric curves, it seems, as far as I can judge them, that there is no signature of hexagonal phase transition there, that it's rather protein denaturation happening above 40 degrees Celsius. Although I don't think it's resolved.
Well, another very question. But I think we'll move on to the next speaker, and if you guys don't mind, we can go over a coffee break for your question, if that's okay. Well, thanks.